Hello students, welcome to engineering assignments. In engineering assignments, today we are going to deal with gradient descent algorithm. It's the second part of gradient descent algorithm video. In the last video, we have discussed the equation of cost function, what is the definition of gradient descent and all. So here I'll give you some examples, I'll give you the algorithm as well as the type of gradient descent algorithms. Okay, so before you watch this video, I would recommend you to watch part 1 of gradient descent algorithm because it is a continuation of that video. You know that cost function is the error function. You know the equation for that. So cost function implies how much error has come from your hypothesis. The hypothesis can be a mathematical formula or a curve or equation that can convert your input data into output prediction. In case of linear regression, it is a straight line. Okay. For the time being, let us consider a mountain and a person standing on the top of the mountain. Top of the mountain is a place where there is maximum error. So our person want to climb down and this person's ultimate aim is to reach the valley. Is similar to reducing the error in case of machine learning. Now, this person will start from the top of the mountain and he will start moving downwards. When he reaches here, say a point A, he checks whether he has reached the valley. No, he hasn't reached the valley, so he will iterate one, two, three step downwards and he will check whether he has reached the valley. No. What he will do again? He will again iterate downwards. And after each and every iteration, he will reach this valley finally. So if you resemble this with a gradient descent algorithm, it's a place where there will be less error. Okay. Now you look here. This is an graph which is given. Here you can see it is the actual value. So here what we will do is we will draw one line and we calculate y bar is equal to mx plus b. Okay, and we check for the error. When we check for the error, you can see that the predicted point, that is yi bar, is very much away from the actual value. Fine. So what we will do? We will again calculate yi by updating the parameter or finding the parameters of m and b once again. So we will draw that line once again and we again calculate yi bar, which is equal to mx plus b, and you check for the error. There is now also some errors are there, but not as here. Here you have so much of error. So once again what it will do, it will once again iterate and it will find out another yi bar. Yi bar is again mx plus b. So you'll find out or you'll update another m value and b value. Then also error is there. So we'll again iterate and find out one more line, that is yi bar is equal to mx plus b. Now you can see that the error is very less here. So this will be the best fit line, or it will be the best hypothesis, we say. This is the principle behind our gradient descent algorithm. Now I hope it is much more clear to you. From all this example, you might have understood what is gradient descent all about, what is the basic principle behind it. Now let us come to the point, that is we are taking a 2D plane where fx is equal to x square. The curve will look as such. Okay. So first we will take a point here and this is the place where you have minimum error, or this is the minimum. Now from here we'll descend downward and from here this is the gradient of this particular curve. It is obtained by calculating the slope, and slope is place where you have the gradient. Again we go downward, we'll check whether we have reached the minimum. No. Again we will go down, again we will go down, again we will go down until we reach a minimum point. The gradient is actually the slope of the curve at a given point in a specified direction. and the slope is obtained by taking the equation of the slope, that is delta y by delta x. So this is obtained by taking the derivative, and we will descend downwards until we get a minimum error. So let me summarize the procedure. In gradient descent method, we start with the initial guess. So we have started with the initial guess by updating the parameters until it reaches the best answer or it converges to minima. So we go on updating the parameters until we get a best answer or it converges to minima. And each iteration, the algorithm takes a step in direction of the steepest descent. Now, a new value which you are going to get will be old value minus step size. Step size is a combination of learning parameter and the slope. So I told you we have to take slope at that point. Also a learning parameter will be taken. So learning parameter or learning rate is the size of the step we must take. Okay, it's the size of the step we must take is decided by learning parameter. And learning parameter is basically we take 0.1. So it will go like this. So if it is other than 0.1, it will go like this. Okay. So new value will be depending on the old value minus step size. From this, it is clear that the learning parameter has the major importance on moving towards the steepest descent. Okay. Now, in case of a univariate function, it is simply the first derivative at the selected point. But if you have multivariate function or multiple variable, it is the vector of the derivative in each main direction. Because we are interested only in a slope along one axis, we don't care about any other. These derivatives are called as partial derivatives. Last time we were dealing with the univariate function, that is fx is equal to x square. Now we are going to deal with multivariate function, that is fx comma y is equal to xy square plus x cube. Now we take the partial derivative with respect to variable x, also with respect to variable y. So here, if you take the partial derivative of x, similarly, we take the partial derivative of y, we'll get this equation. So this is the gradient function of f x comma y. This implies that the rate of change of function at a given point and in higher dimension function, the gradient is considered as a slope. So what all this gradient will give? The gradient will give the direction of maximum rate of change. The magnitude indicates the maximum rate of change, and the point in the direction of the steepest increases in the objective function. Objective function is a function we want to minimize or we want to maximize. Here we are minimizing the cost function. So when we are minimizing it, we call the objective function as cost function, loss function, or error function. Now I'll go and see the algorithm. So gradient descent algorithm for linear regression. So linear regression, you know the equation is y is equal to mx plus b because the hypothesis is always straight line. So initialize the coefficient of m and b. See, when we are starting, we are taking a random value of m and b. We take m is equal to 1, b is equal to 2. And then the equation is y is equal to 1 into x plus 2. And we can see that it is not a best fitted for historical data. See, because they are very much scattered. So it's not best fitted line for historical data. So what you have to do, you have to compute the gradient. For this, we have to use the sum of squared error as a loss function. So total SSE is equal to 1 by 2 y minus y bar the whole square. Instead of y bar, I am going to substitute mx plus b. Therefore, we take the partial derivative. The partial derivative with respect to m is minus y bar into x. With respect to b is minus y bar. Now what we have to do? We had already chosen initially b and m. Now we have to update the coefficients in the direction of optimal m and b. So new m will be old m, what we have taken as initial one, minus r into the partial derivative. R is your learning rate. Similarly, b is equal to b minus r into the partial derivative. Okay, so you'll get the new values of m and b. Now use this new m and b for prediction. Calculate the SSE at each point and find out the total SSE. which is the sum of squared error of the data points divided by 2. So total SSE is equal to 1 by 2, sigma is equal to 1 to n, y minus y bar the whole square. Repeat step 2, 3 and 4 until optimum value for the coefficients m and b are found, and that reduces SSE to minimum value. Now optimal value of m and b will enable the model to predict the y with highest accuracy. So same thing what I've told before is written as a point. That is, this operation is called gradient descent and works by starting with a random values for each coefficients, that is your m and b. The sum of squared errors are calculated for each pair of input and output values. The learning rate is used as a scale factor and the coefficients are updated in the direction of minimizing the error. The process is repeated until no further improvement is possible. When using this method, we select a learning rate. It is denoted by alpha. In some textbook, it's denoted by R. That determines the size of improvement step to take on each iteration of the process. And this process is repeated until the cost of the coefficient is 0 or it's close enough to 0. Now, different types of gradient descent. One is batch gradient descent. To calculate the gradient of a cost function, we need to sum all the training examples of each step. So, if you're taking all the training example at the same time, it is called as batch gradient descent. And after taking the sum of all training examples, we update the model. The model updates and training speed may become very slow for large sets. See, if you're taking millions of data and if you're taking sum of all the data together, it will become slow. That is, it refers to calculating the derivative of all training data before calculating an update. So it will become very slow. So there is another gradient descent method, that is stochastic gradient descent. We use one example or one training sample at the each iteration instead of whole data set and taking sum at every step. And it's widely used for large data and computationally is very faster and can be trained in parallel. And one thing we have to do is we have to randomly shuffle the training point before calculating it, and frequent updates give an insight into the performance of the model, but it may result in noisy gradient signal and it will become hard for the algorithm to settle on an error, which is minimum for the model. And it refers to calculating the derivative from each training data instance and calculating and updating immediately. So here, because of the noisy gradient signal, we go for another one, that is mean batch gradient descent. So here it will split the training data into small batches and it's used to calculate the model error and update the model error coefficients. So batched update provides computationally more efficient process than your stochastic gradient descent, and here the error information accumulated across a mini batch of the training examples like batch descent gradient algorithm. So that completes the whole class of gradient descent algorithm. I hope it is clear to you. Thank you students. Thank you for watching my video.